There are lots of fantastic magical items in the world of Harry Potter. Flying brooms, self-cleaning dishes, whatever this thing is. Anyway, most of these can only exist in a magical world. But I can think of one that has some promise. We're going to take some robots, some AI, and a really powerful computer, and we're going to make a real Marauders map.
This map shows
everyone.
Everyone?
Everyone. Where they are, what they're doing every minute of every day.
Brilliant.
Thanks to a bunch of my local hardware store has had to put up a whole bunch of new security cameras. That was a giant pain for them, but works perfectly for this project. With over 50 cameras in the main area alone, we can use those video streams to keep an eye on the entire store. When we did the Weed Killer project, we had to go around and create our own neural network for detecting weeds in the yard. But since people are a really common thing to find, we can use a network called PeopleNet. It already exists and has been trained to be able to find people in video streams. That doesn't automatically translate to where they are in the store, in the real world. The first thing we're going to need is an accurate map of the store. We could use the drawings that were used to create the store and lay everything out, but we have no real reason to assume any of that is accurate or that it hasn't changed. So we need to create our own map. We're going to use something called SLAM, or Simultaneous Localization and Mapping. SLAM works in a loop. The first thing the robot will do is take its estimate of where it thinks it has moved, which is called odometry, and it will estimate where it thinks it's in the map. Then, based on what it can currently see around it, it will adjust its location to find where it actually is in the map. Then, it will take that data that it sees and add it into the map. It will then repeat this over and over again as it's driving around. We're using a ZX stereo camera from Stereo Labs and a Jetson or an AGX on top of the Hunter SE from AgileX. We'll set all of this up on Hank and take it to the store and record a path driving around. Normally you could make a 2D map using just a 2D laser, and that would work in what are called unstructured environments, like outside or rooms that are kind of random. But in a space like a store, that won't work very well because all of the rows are lined up evenly, they're all evenly spaced, all the same length, and so just based on 2D data, the mapping algorithm will get confused which row it's in, and it will very likely make a terrible map. So that's why we're using 3D data. This has a lot more data, which needs more processing, which is why we're using the Jetson, but it will help the robot not get lost because, yes, the row is the same shape, but each row has different objects in it, different colors, different spacing of items, and so the SLAM algorithm shouldn't get lost as easily. To be able to tackle a map of this size, we need a really solid workstation. And for that, we're going to be using the Z8 Fury from HP. This thing's an absolute beast. It has 500 gigs of RAM, 2 A6000 GPUs, and a 60-core CPU. And it has dual redundant power supplies, so even if one fails, the system will just keep running. It's meant for doing things like fluid simulations, FEA analysis, working with really large data sets, really complicated 3D models. This is the kind of system you would want to use. We're creating the map using something called RTAB Map, which is an open source software for creating 3D maps from something like point cloud data like this. This is a really large space at 35,000 square feet. But once it's done, we can export that map as a point cloud, which then we can bring into Blender. Just opening the mesh file in Blender takes over 130 gigs of memory, which is insane. But at 500 gigs, it's got more than enough to spare. Now that we have an accurate measurement of what's really in the store, we're going to simplify it. We're going to aim to be pretty close. We'll put in all the shelves and all the displays so we know where everything actually is in the store. And we can just render this as a 2D map. So we have our map and we have our video streams. We need a way to marry these two together so that we can relate an object's position in a video stream to a position within the store. From NVIDIA, they have something called the calibration toolkit, which is meant specifically for doing this. You put in your map and you put in just a still frame of your video feed. You select locations within the video stream, then you mark where they are on the map itself. You can use something called OpenCV to take these positions and create something called a projection matrix. That makes it so that any point in the video stream, you can easily calculate where that position lines up in real world space or in the store. We can find people in video streams and we can find where those people are in the store themselves. But there's still a couple things we're missing to get to full map. The next thing we need to tackle is how do you handle all of these video streams at one time? Normally when you handle something like this, you receive a frame from the camera, you then copy that frame onto the video card's memory. Then in the memory of the video card, you run it through a network that will find the person, and that will return that data off of the video card to the CPU. Then if you need to run it through a second network, say if you wanted to see if the person was happy or not, you would take that image again, you would crop out a subset of that, copy it back to the video card, run it through a second network, and then get that data back to the CPU. All of that moving around of data is not terrible if you're only working with one video stream or one image. But if you're handling 40 video streams all at the same time, that's an absurd amount of data that you need to be processing live. This is where we're using a framework called DeepStream. It's made by NVIDIA, but it's meant to handle high volume data streams like this. It keeps all of the data in the GPU memory so the GPU can process it super efficiently. One A6000 video card has enough memory to store all these video streams at once, but it doesn't have enough processing to be able to process all of these at once. And that's why it's good that we have two. So we can take the video streams, split them in half onto each video card. Each video card processes them in parallel, then assembles it at the end, and then sends out the results. We still need to be able to actually track individual people. We want to know where that person is and where they came from, so we can actually create a path showing where they went. And this is the next step in the DeepStream pipeline, which is the tracker. The tracker will take what the detector found and compare it to what was previously found. If they're close enough, it will say this is the same object. And you can track not only that same object from one frame in the video to the next, but you can actually track it from one video stream to the next. So you can track where this object is moving across the entire space. Using PeopleNet to find a person in a video stream works, but it's not accurate, since it's assuming that the person will fit inside a vertical rectangle. on the video stream. But because the video is actually a bit of a fisheye, if they're kind of off to the side, the person looks like they're standing at an angle, but PeopleNet won't get that location accurately. We're going to use something called a pose estimator. This is more than just recognizing a person, but it's actually recognizing the shape of their body, knowing roughly where their feet and their joints are, their head, and from that, you can more accurately estimate where the center of their body is on the floor. This step is actually done as part of the tracker. It uses the video's calibration as part of the process to find people more accurately. And since it knows where the people are now in the store, it can use that more accurate tracking to track between video streams. The video streams come in and are split into a batch for each GPU. The detector will find people in the different video streams. The tracker will then find more accurate positions for each person and compare to find the path that they took to get there. The positions are sent out of DeepStream into a Python program that will draw not only the current location, but the path the person took to get there. We make the map look a little bit fancier, swap out the basic path for actual footprints, and we have a Marauder's map. Let's get Stanley dressed up as a person to give the object recognition a real challenge.
There we go, now we're rolling.
I believe the British call this snogging.